Hello, my name is Emiliano Cantu Samaniego, and I'm part of the Autonomous University of Nuevo León in Mexico, and also part of the Faculty of Chemical Sciences. I am part of the research team focused on the synthesis of MAX phases and 2D MXENE phases through solid-state reactions in air using molten salt sealing. Okay, MXENEs represent a new class of two-dimensional materials endowed with unique properties suitable for a wide range of applications. The max phase synthesis process involves a solid-state reaction at a high temperature ranging from 1100 Celsius degrees to 1400 Celsius degrees in an inert atmosphere. On the other hand, the synthesis of MXENE involves selective etching on the A layer in the max phase using highly concentrated and toxic hydrofluoric acid, or HF, in this study we propose a novel approach that employs molten salt assisted solid-state reactions instead of the HF for both max phases and MXENE phases. For the synthesis of max phases, such as MB2SNC, the precursors were sealed with molten salts using KCl and AACl respectively, and subjected to an oven environment ranging from 700 to 1000 Celsius degrees while exposed to air. In the left side of the poster, you can identify the reaction that is taking place while being in the oven using the max, in this case, conformed of MB2SN and C, with the molten salts being KCl and AACl. This process is being given at 750 Celsius degrees for around 12 hours. MB2SNC max is obtained after this process, and we proceed to dry it in a sealed oven. By doing this, we can identify in the SEM studies and images corresponding to the MB2SNC max that the layers are forming. Even though it is not a perfect formation, we can see the effectiveness of the new process without the harm of using hydrofluoric acid. Also, the XRD analysis is selected at the end of the left side of the poster. In the other way, by the synthesis of the MXENE phase using MB4AlC3, we use CuCl and also the molten salts such as KCl and NaCl to the same furnace conditions, 750 Celsius degrees for 12 hours. By doing this, and also by applying different washing methods using HCl by distilled water and distillate water, we can obtain a better result than with the max phase. As we can see on the SEM images corresponding to the MB4AlC3, we can see the different layers and nanostructures being formed with this process. Again, without using the hydrofluoric acid. So this process is way safer than the old way to do it. And also by analyzing the XRD adjacent to the figure 4, we can understand that the XRD pattern confirms the analysis of MB4AlC3, confirming the hexagonal max phase and the XRD pattern that is formed by the formation in the MXENE, in which the peak corresponding to the AL around 37.2 degrees has disappeared. Also, in the left side of the poster, we can see the XRD pattern, or MB2SNC, that confirms the formation of hexagonal crystals structure max phases, which is in line with the standard ICSD files reported. By doing these studies, we can conclude that in the field of electrochemical sciences, MXENE's excellent performance is enough to replace graphene in the construction of electrochemical sensors. This also gives a lot of hope in the new field of storing energy for different renewable applications. Max phases, such as an analysis of MB4AlC max and MB4C3 MXENE, were synthesized using precursors of seal with molten salts, which gives more security to the process and also adds a novelty to this already researched topic. We have developed deeper deeper connections with the help of microlens to a two-dimensional scale, providing us with the different data of the HV, MAG, and SPOT. In the sensor, we can see that around 1 to 3 micrometers limit of detection, we can identify the layers forming, which demonstrates the excellent recovery and adequate percentage. So, by concluding, by etching the MXENEs without the HF, we can produce a high yield that is not hazardous due to the highly toxic and corrosive nature of HF. Thank you very much for your attention. I hope you find this interesting.